Hello everyone, thank you for being here to listen to our presentation. Our project paper is about instrumentation and stream monitoring of BFRP or basalt fiber reinforced polymer bars in pedestrian bridge deck Link-Slab. I'd like to acknowledge my colleagues, Dr. O'Keel, Dr. Fletcher, Fowler and Jones, and Mr. Nolan from Florida Department of Transportation. Let me start with the presentation outline. We're going to be talking about the introduction, the background of the project, the benefits of the project, the objectives, and the field investigation that we conducted, and the results and the analysis, and then we'll end that with the conclusions and recommendations. As far as the introduction, we just wanted to highlight that eliminating expansion joints in bridge decks is considered a good alternative since most joints leak and the debris is accumulating, and we wanted to address this issue and reduce the maintenance and improve the bridge deck life expectancy in general. So that project of Link-Slab or jointless bridge deck, it's one of the good alternatives to tackle the problem with deficient bridges, and one of the best solutions that we're having, since the bridge deck joints are costly to buy and install and maintain, and they've been constantly the joints have been constantly providing severe performance and maintenance problems. So using the Link-Slab to make the bridge girders partially continuous or continuous only for the lateral longitudinal load effects is providing improved seismic performance and durability. It's also providing better resistance to wind loads and storm wave loads, longer spans, lower cost, and better riding quality and improved structure integrity for our bridge. So this Link-Slab with basalt fiber provide a promising alternative that we wanted to highlight and present and conduct. The background of this is the bridge decks, as we mentioned earlier, are costly and leaking and causing all these kind of problems. But the aim of our project is basically, or the background is that we wanted to conduct that project to monitor and investigate the performance of the Link-Slab of a pedestrian bridge that's reinforced with basalt fiber reinforced bars. And the Link-Slab, we knew that is going to eliminate the future risk of degradation. There was another follow-up project that was conducted that's not part of our paper, but it's using ultra-high performance concrete for the Link-Slab as well. Our good research team investigated this simple span concrete girders that are made continuous by creating continuity Link-Slab between the girder ends. And we investigated the performance of that Link-Slab and monitored the performance of the basalt fibers embedded in the concrete overlay that is supported by FSB or Florida slab beams for a two-span pedestrian bridge along the US 41 over Morningstar Waterway bridge in Florida. And I'm just sharing with you that the support conditions itself at the ends of the girder, whether it's hinge or roller, play a significant role as far as force is developed in the Link-Slab, the gap opening between the adjacent girders. And here is a sketch that's showing the process of installing the Link-Slab for existing bridges, like so cutting the concrete deck, the deteriorated concrete deck, rebarring and casting continuous deck on top of simply supported girders, provided that we have the bonding between the ends of the girders and the Link-Slab. So the project benefits that we're seeing here is that eliminating the purchase of joints and bearings and smoother riding surface, lowering the initial cost, and enhancing the riding quality of bridge and enhancing its integrity, and that is eliminating so many problems that we have. The objectives of our project, as we mentioned earlier, is having the Link-Slab over FSB or Florida slab beams and providing recommendations for instrumentation of Link-Slab and suggestions for the monitoring plan and suggestions for the instrumentation system to monitor the temperature, strains, and elongation of the Link-Slab. That was basically the objective that we're having. To get to our project, as you can see here, these are the two simply spiral girders of pedestrian bridge and the concrete deck cast on top of it. The bridge has been instrumented by two types of sensors, surface mounted and embedded sensors at the same time. And we monitored and evaluated the performance of the Link-Slab during and after concrete casting. And we used several sensors, including the vibrating wire sensors and with integrated thermistor. The good research team installed the sensor strategically on both sides of the middle or the midline of the Link-Slab, and that is to detect and capture the strains in the basalt fiber bars and the strains in the concrete Link-Slabs and the movement of the gap between the adjacent girders. The data acquisition system, let me show you the next slide right here, that's showing the sensors and everything. So the data acquisition system, which is in the side of the parapet wall, as you can see right here, recorded the strains and deformations at regular time intervals. And the research investigators measured and monitored the deformation, the strains, and the cracks developed in the Link-Slab. The data has been collected during service over 2 periods. Each one is like 3 months each, actually. And the capture data was related to temperature and shrinkage of the concrete and did not include any significant live load effects, since there was no load testing performed on the bridge. And the measurements corrected for temperature changes, and we investigated and evaluated the instrumentation data and analyzed the results and provided conclusions. So I just wanted to share that with you. As you can see right here, these are the details of our sensors that we used, and it was really interesting project for us. The next slide is just about the data acquisition system. As you can see here, we had embedded sensors, and that is instrumented. It's connected to the data acquisition system, and the sensor was like 18 of them. So we had 18. So let me get back to here. We had 18 embedded sensors. That's 3x3 arrays of strand meters and sister bars. And it's like 9 pairs of embedded sensors of strand meter and sister bars. 9 deformation and strain sensors of strand meter. They were clamped to the Link-Slab, and for the longitudinal reinforcement, and 9 strain sensors for sister bars that's fabricated on number 4 epoxy coated steel reinforced bar was used. And usually there's a standard length for the standard, it's like 36 inches, but for the sister bars, but we adjusted that to 31 inches to fit our setup in that bridge. And as you can see, here is a layout for the location of the embedded sensors and the arrays that we're having, and the top view of the embedded sensors as well. The strand meters and sister bars were used. The strand meter was used to measure the deformation and the strains in the reinforcement. However, the sister bar was to measure the strains in the adjacent concrete, in the concrete approximately the same location of the bars. Just to highlight the time frame, the first set of data was recovered in November of 2020, and that included the data from March of 2020 till August of 2020. Then we had the second set of data, which was recovered in February 2021, and that contained the data from November of 2020 to February of 2021, and the data was recorded once every hour. Here is our data acquisition system, and that's included the 2 Geocom brand data loggers, and each of this unit was capable of monitoring input from up to 16 channels, 16 vibrating wire cables for 32 inputs. The data logger power was supplied by either 4 alkaline D-cell batteries, and another option also there is 12 volts external grid supply. And the data acquisition system was installed, as you can see here in that figure, bottom right at the outboard side of the southwest, facing the parapet wall near the midspan of the bridge. And the data logger were housed inside a fiberglass or weatherproof rather enclosure, and the wiring is secured as well. And then there was a software called LogView software. It's interfacing with our data logger, and we recorded the data of the sensors, and the data was accessed and downloaded by direct retrieval at several times on our bridge. The data that we have for the deformations and the strains, strand meter was recorded, and the initial reading was calibrated and input in the data logger and used to calculate the output. And the output from this data logger for the strand meter was in millimeter of deformations, and obtained through a certain equation that's in the paper, and the equation used to correct the effect of temperature. And after correcting the deformation and temperature effect, it was used to calculate the strains in microstrains. That was for strand meter. For the sister bars, the data reduction for the sister bars, the output data from the data logger for the sister bars in the data logger is in microstrain, and they were obtained by also an equation that's in the paper. The initial reading calibration factor were entered as input in the data logger, and then from the apparent strain, the temperature corrected load related strains was determined, and load related and the actual strains were recorded as well. I just wanted to show you that that is the data that we're having. And the strand meter and sister bar were installed before the Link-Slab was cast, so the sensors were exposed to thermal effect. And in order to determine the concrete deformation and strains after the concrete was poured, the data was zeroed and shifted to start at hour 92. We plotted the graphs, and the average daily strains and the mid sensor appear constant from 9 days on. And there has been some outliers and daily changes for the maximum differential that could be attributed to some electronic systems in the vicinity of the sensors, or caused by data acquisition system glitch that's causing some spikes. We addressed that. It was noted also that there's some cracking being developed in the middle of the concrete Link-Slab, which is expected over the pier support, and that's where we experience the high level of the strain deformations. The maximum strain calculated in the strand meter was around 600 microstrains from the mid sensors, and the maximum strain calculated from the sister bar was around also 600 to 700 microstrains in the mid sensors as well. The strain were small compared in the BFRP, were small compared to the ultimate strain level of the BFRP. And after approximately 90 days, the average strain recorded did not significantly change, indicating that minimal creep or shrinkage strain was experienced. The maximum daily strain changes was about 500 microstrains, and these are the data that we're having. And it was great. And let me come to the conclusion that we're having, that the Link-Slab showed good performance and give us an insight into the stress developed in the Link-Slab. And that is due to thermal temperature changes. The Link-Slab performed very well without showing any excessive cracking, and the strain developed was from around 600 microstrains, and that is small compared to the ultimate strain of the BFRP. After 90 days, the average strain in the mid joint did not change significantly, indicating that minimal creep or shrinkage restraint was experienced. It's recommended that you use BFRP bars in the Link-Slab. So that was really a good outcome for our project, and that encouraged us to even go to the ultra high performance concrete. Our recommendation is that further investigation should be conducted to monitor the long-term performance, and also to monitor the live load test effects using load trucks. Also, using ultra high performance concrete should be investigated as well in future research. With that being said, I really thank you so much for listening, and we're so happy that we conducted that research project that took us like over a year and a half to monitor. Thank you so much for listening, and I'll be glad to answer your questions. Have a great day.